welcome to, let me just double check, make sure everything's going. Okay, looks good. Welcome to chapter 1 of Math 103 for Global Community College. Let's begin. We're going to start with some pre-algebra work and then go in. I will hopefully be annotating on the screen as we go. Let me double check, make sure this works the way I think it does. Yeah, that looks good. Sweet. So we will go through the chapter. I will, when the text prompts it, I'll go through examples here. This is meant to be a companion, not a total education. Of course, you can always leave comments about your questions or kind of whatever works best for you. Yeah, let's begin. So we're going to start with a pre-algebra review for chapter 1. And this is a variety of things. We'll include in this an introduction to integers is where we're going to start. So the book, I think, does a pretty decent job of letting you know your objectives for each section. And those, I think, are useful for kind of knowing where you end up at. So in this one, objectives include inequalities, opposites, and absolute values. Essentially, what is a number? And the book thinks a good way to describe what numbers are is through set theory. Set theory is the word used to describe things or existence in mathematics. Long story short, food groups are an example of a set. You can say vegetables, right? And the set is vegetables. Everything inside the set would be all the vegetables. So, a hamburger is not a vegetable. So hamburger is outside of the set of vegetables. Cucumber is a vegetable. So cucumber is in the set of vegetables. That's what a set is. And this is useful in mathematics because they can define what things are and what things are not and how they interact with each other. They talk about here the roster method of writing things in a set. This is math theory, most of the work we do in the class, but we're just laying down the very basic groundwork principle of mathematics here. So we can look at the middle example there. If I give you a list of numbers 1, 2, 3, 2, 3, and I ask you to describe the set of those numbers, well, the set would be just 1, 2, and 3, because the set is everything that's inside of it, right? If I give you 5 cucumbers, that's still a set of vegetables, regardless if there's 5 cucumbers or 1 cucumber. So things being repeated in math is fine. Essentially what I'm saying. The fact that you have more than 1 3 when you're counting stuff doesn't change what 3 is. You got that little E down there. That's a Greek symbol, I believe. It means you include it in a set. Again, this is high-level math. But we're just kind of breaking down the basics of these conversations for you. We get to this. The first application that's useful to us is defining numbers. The first thing we're going to do is a natural number. A natural number is essentially a countable or a counted number. And what that means is the real world things exist. And the real world, you count what exists, right? You can't count 0. Because by definition, in order for something to be counted, it needs to be there to be counted, right? I can't say I can't count 0 pieces of paper. There just is 0 pieces of paper. And so what this means, again, natural numbers are, as is shown there, 1, 2, 3, 4, 5, on. Noteworthy here, natural numbers are not fractions. Natural numbers are not decimals. And natural numbers, as stated as well, are not negative. You can't count a negative number. You can't count quarters, right? You can't count a quarter of something. That's 1 itself is that piece. So if you got a pizza pie, right? You got a pizza, you cut it into 4 sections, you count those 4 sections, 1, 2, 3, 4. That is your set of pizza slices. And then that's also 1 pizza. So if you change the set, then what you're describing changes. Are we talking pizza slices or pizzas? And that's what a natural number is. Again, just math theory at this point. Another set of numbers that we can deal with is what's called integers. Integers include negative numbers, but do not include decimals, fractions, stuff like that. Negative numbers, of course, are useful. They just, and as we'll get to in a bit here, they describe the other ways. If you're increasing, it's positive. If you're decreasing, it's negative. Negative numbers, of course, are actual things, right? Temperature be an example of that. You're going to have negative temperature because we set a 0 at some point, and everything above 0 is positive, everything below 0 is negative. It's just a direction of how to do things, as shown in this line here. Negative numbers are the opposite direction of positive numbers, and zeros, and the 0 sits between the positive and the negative numbers. I think that's a really good way of thinking about numbers and math in general. Negative isn't a statement of quality, right? Negative is just a definition of what we're talking about. And that's, again, why we start with set theory, because it's important to look at everything at math as exactly what it is, not add any flavor to it, and just run it as B. So here we can see -3 is shown on the number line and 4 is shown on the number 9. So we can use these in math equations. We know that -3 is 3 steps away from 0 and +4 is 4 steps away from 0. So how many steps are there between -3 and 4? Well, you can count them, right? Or you can use the phrase I just said. If -3 is 3 steps away from 0 and 4 is 4 steps away from 0. So how many steps are there total between them? Well, there'd be 7 steps between them because there's 3. You got to step 3 to hit. You got to step 3 times to go from -3 to 0. Then you got to step 4 times to go from 0 to 4. That's what's going on here. The phrase we use in math to describe things is a variable, and basically a variable varies, changes. A variable is something that's not defined. So -3 and 4 are defined, therefore they're not variables. A and B in these examples here are variables because A and B can kind of be anything. An example of using a variable as shown here would be inequality symbols, less than, greater than. You have 2 of something, I have 4 of something. Is my stack larger than yours? Yes, therefore my stack is greater. But 2 and 4 are just numbers I chose. I could have done -5 and 50,000, right? And A and B can be any numbers I want them to be because they're variables. I define A and B as variables, therefore anything can work. And of course, the way to remember which sign is the greater inequality symbol, which sign is the less inequality symbol, I always suggest using the alligator analogy. The alligator always wants to eat the bigger thing. So A is less than B. We'll go over here. A is less than B because the alligator wants to eat B. A is greater than B because the alligator wants to eat A. There you go. And if you want, always put little teeth on your inequality symbol to remind you they are in fact alligators. See? Yeah, isn't that useful? All right, let's move on. Number lines, using what we're talking about here. If I write down a number line and I put 2 dots on it, in this case, -2 and +1, and I say, well, -2, is that greater than or less than +1? Well, the left is less and the right is greater. So -2 is to the left of 1. So -2 by definition is less than 1. So the alligator wants to eat 1. There you go. You could also use the greater than or equal to symbol, which is putting the bottom half of the equal sign under your greater than or less than sign. And it allows the question to be answered as an additional option, essentially. What is 6? Is 6 greater than, less than, or equal to 6? Well, 6 is equal to 6, so I can use the greater than or less than or equal to symbols to define that. And this all may seem pointless in the context of like everyday applicability, but math very much works in steps, and you have to start at the bottom and work your way up to the top. So getting this super basic stuff down, this might actually be useful to you. I don't know, but understanding the most basic level of mathematical theory and numbers and how they work and how we use them will let you do more advanced, more difficult things later on. So use the roster method to write the set of negative integers greater than or equal to -4. So what is that? Well, they show the solution on the screen. I kind of hate when they do that, but let's break down that question so I understand what we're doing with here. A set. What is a set? A set defines something. Okay, cool. Negative integers. What is negative and what is integer? Well, so let me highlight this stuff real quick. We got set. We just defined set. That's a group of something. Negative, meaning opposite of positive. The way we define negative, of course, is with a negative symbol, which is that guy there. Integers, those are numbers. Those are not decimals. Those are not fractions. They can be negative, can be zero. Cool. That are greater than or equal to. What's greater than or equal to mean? Well, on the number line, we need to move to the right, or the numbers need to increase, right? Of course, you can think of temperature as well. So if it's -4 degrees outside today, it's -2 degrees outside tomorrow, the temperature increased, right? It could be 78 degrees outside the following day. Those are both increases from -4. It's not saying how much it increased. That's not the question. Just that it is warmer, it is bigger, it is larger, it is faster. These are all greater thans. So we need a set of negative integers greater than or equal to -4. What's equal to? Equal to means the same, right? So what is -4 equal to? Well, -4 is equal to -4. Cool. What is greater than -4? Is -5 greater than -4? I wouldn't say so. If it's -4 today, -5 tomorrow, the temperature not warm up, it cool down. So -5 don't work. -6 don't work. -7 don't work, right? We're going the wrong way down the number line. So let's turn it around and go the other way. What numbers are to the right of the number line of -4? Well, -3, -2, -1, right? 0. 0 is also greater than -4. So it's 1, so it's 2, so it's 3. But 1, 2, and 0, 1, 2, and 3 are not negative. So we can't use those. What about -1.7? Okay, that's greater than -4, but it's not an integer. So we can't count that. So the only things we can count to answer this question are the solutions shown there. Let's move on. The use of opposites and absolute values. So as I was saying before, a negative is an opposite, right? 4 and -4 are both equal distance from the center point on the number line, or in this case, 5 and -5. So they are opposites of each other. If you want to be a fancy math word, you use additive inverse, same difference. 2 and -2 are opposites. So the important thing to take away from this all is that's what the negative symbol means. That little line right here, that means opposite. So if I have the number 2 and I put a negative in front of it, it's saying it's the opposite of 2. So -2 is the opposite of 2. So what if I take a -2 and I put negative sign in front of it? Well, what's the opposite of -2? +2. That's what's going on there. And then the absolute value of a number is, in practice, the positive number, but as a strict definition, it's the distance from 0 that the number is. So the absolute value of anything is a positive number, even if it's in the negative direction. Which is what's shown here. The absolute value of 3 is 3 because 3 is 3 steps away from 0. The absolute value of -3 is also 3 because -3 is 3 steps away from 0. That's like the definition of it. In practical terms, the absolute value of something is just its positive version. say something is absolute value by doing these vertical bars on both sides of it. That's how you know an absolute value. And you can see from the examples down here, absolute value of 0 is 0. 0 is weird. Don't think about it too much. Cool. So what am I looking at here? Well, part of math, and we'll learn this as we go through the chapter, is figuring out what I'm looking at and translating into something I can understand. So let's break this down a little bit here. What do we have? We have horizontal vertical lines. Those are the opposites, right? So this and this are opposite. And then we have vertical lines here and here, which mean absolute, ABS, absolute. And then we have a number that looks like the number 12. Cool. So we can, well, where do we start in solving this problem, right? That's something we'll get to later. Let's, for example, for this here, start from the number and work our way out. So we start with 12, that's number, cool, and then we have a negative sign in front of it. So that means the opposite of 12. What's the opposite of 12? Well, the opposite of 12 is negative 12. Cool. And then out beyond that, expanding out, backing up, if you will, we have our absolute value on the outside. So what is the absolute value of negative 12? Well, the positive version, remember the absolute value of negative 12 is 12. Last thing we have here is this another opposite sign, which is throw in the front. What's opposite of 12? Negative 12. So the negative absolute value of negative 12 is negative 12, right? We could have solved that. I'm gonna do a different color here. We could have solved that from the outside in as well, I suppose, right? We start with a negative number, so we know something's negative. Then we have an absolute value of something inside. The absolute value of the thing inside is negative 12, which makes it positive 12, which then makes us a negative number to give us negative 12 again, right? You can solve it both ways, figure out what works best for you. A lot of this class is going to be focused on kind of giving you the tools rather than you memorizing stuff, right? To that extent, I want you to look at these things and figure out a way that works for you and follow that procedure up until it doesn't work for you. And then we'll talk about changing your methodology. At this level, if it works for you, do it. I'm going to skip through some of these examples, not do them because I don't want this to be a follow-along video, right? But since this is a YouTube video, feel free to pause it, solve it, move it on, make sure you understand. All right, so next we're going to add and subtract and do some application problems. Cool. So, as we said before, a number line is a good way to visualize what numbers are. A positive number is to the right of 0, a negative number is to the left of 0. Likewise, increasing or decreasing a number is simply moving on that number line. If I have a number and I want to decrease it, make it smaller, I move to the left. If I have a number I want to increase and make it bigger, move to the right. Again, you can think temperature as an example here. So, what happens when I move to the right? When I move to the right, I am adding to the number. Addition is the term we use to move to the right on the number line. Technically, the numbers being added are called addends, and the total is the sum. You probably heard summation, sum before, right? Addends, no one cares about. So if we start someplace, let's say we start with 4, that means we are 4 steps to the right of 0 because 4 is not negative 4. Negative is to the left, positive to the right. We start at 4, so we move 4 steps. We add 2 more. We end up with a total of 6 steps away from 0. There we go. All right, so we start here. 1, 2, 3, 4 steps. Pretend those are equal size. Plus 2 more steps equals 6. Yay! This works the same way every single time. If I start at -4 and I move 2 steps, I end my journey at +2. You can go back and forth as long as you're moving to the right, you're adding. This is beneficial because it explains why adding two positive numbers is positive and adding numbers that are different signs. A sign is positive is a sign, negative is a sign, right? So if you add two numbers, you're doing something positively because you're moving to the right both times. If you add negative numbers, you're moving to the left because the opposite of moving to the right is moving to the left. In the same way that 4 and -4 are opposites because they're the same distance away, moving to the right is positive, moving to the left is negative, no sign. Of course, you probably know the answer already. What do we call moving to the left? Subtraction, taking away, making it colder, all those things. So if I start with -12 and I add -26, I'm adding in the -26, in the opposite direction of 26. So I am subtracting those numbers away. And that can get kind of confusing. I get that. Honestly, majority of the stuff in this class is going to be practice. That's the best way to figure out math, is simply to do it. So let's take a look here. All right, so this first one is just brute force explaining the idea. However, I think the second example does a pretty good job of explaining what a negative number is. Here we are asking you to do -19 plus 8. All right, cool. What does that mean? Well, I start at -19, so I go the number line all the way down the left to 19, and then I move to the right 8 steps. -19 plus 8 is an accurate way of describing it, but it's kind of confusing. The cool thing about math, as it shows here, is we can swap around pluses and minuses in the organization of what we're looking at and not affect anything, because I'm simply a plus sign is moving to the right and a negative sign is moving to the left. That's all it is. So if I move to the right first and the left, or to the left first and the right, that doesn't matter because the end result of the journey is what I care about. That's what's going on with these two examples at the bottom here. This example here, I moved I moved -4 in one direction, I moved 2 in another direction, right? So I moved -4 first, then 2. But if I was to switch these around and move 2 first, oh, sorry, let me erase that, start from 0. If I would have moved +2 first and then -4 later, I'd still end up with the same result. So if I did 2 minus 4, same thing. And that's kind of fun. All right, let's move on. Here's a list of phrases that all mean the same thing: add, more, sum, increase, total, plus. They all mean the exact same thing. They all stand for adding or addition. So let's work on solving some of these problems. Again, I'll do a couple of these. I expect you to do the rest unless you get it, in which case skip over them. So 37 plus -52 plus -14. That's the way I read that. I start from left and read to the right because that's just how you read a book, right? So we'll run that for now. 37 plus -42 plus -14. 37 is a positive number. -42 is a negative number. -14 is a negative number. So opposite of 52, instead of going 52 to the right on the number line, I'm going 52 to the left on the number line. Correct? Cool. So plus means I'm going to add these numbers together. All right. So let's clear that. There we go. So how do I actually approach this? Well, I start at 37, which is I start my number line, I move to the right 37 because 37 is positive. And then I add -52. What does that mean? Practically, how can you explain that to me? Well, 52, the opposite of, right? Negative is the opposite of, 52 is the number. So what is the opposite of 52? Well, that'd be 52 on the other side of the number line. 37 is on the positive side of the number line. Negative 52 is on the negative side of the number line. I'm adding them, which means I'm, walking 37 in one direction, and I'm walking 52 back in the other direction. Negative 14, walking to the left, then walking in the opposite direction of the positive number. Cool. So we can write it this way, that's correct, but as we hinted to earlier, we can rewrite this in something that's a little less cruddy. Like I think actually I have text, don't I? I do have text, cool. We can write something a little less cruddy. For example, I can do 37 minus 52 because, again, adding a negative number and subtracting are the same thing. What do I do when I do that? That equals negative 15. So I'm 15 to the left of that number line. I've passed 0 and kept on going, right? And then I can do negative 15 minus 14. So I start at negative 15, which is the opposite of positive 15. I start at negative 15 and I subtract 14 from that, or I move to the left 14 more to land me at negative 29. Excellent. So happy. Subtracting integers, basically what we just talked about, right? Subtraction is moving the opposite direction of addition. So if I have if I subtract negative 40, I have negative 40, which is the opposite of 40, and I do the opposite of the opposite. What's the opposite of negative? Positive. This turns into negative 21 plus 40, because 40 is my initial number. The opposite of 40 is negative 40, and the opposite of negative 40 is positive 40. I guess I will also just bluntly say math online is difficult. You really, if you're not grasping something, should email me, should comment down below. You should get a hold of me in some way, or find another resource. Here's a bunch of phrases on subtraction. Or you should find a resource that works well for you. If this style of teaching isn't clicking for you, and Khan Academy works better, or reading the textbook works better, do that, please. You're only going to benefit from that. All right. So let's solve this guy and figure out what's going on here. So there's a couple of different ways you can resolve these things. You can just start right out at it, or if you want, you can try to alter it a bit so it makes a bit more sense to you. For example, I have this weird looking subtract negative 21. Well, what's the opposite of negative 21? Positive 21. So I can replace that with a positive 21 and then rewrite my original equation. I really should have did the text version of this. That's coming together. Minus 4. And I've rewritten the same equation, but with less clutter into it. And as you see here from this example, the book suggests, and I would suggest too, if you have only addition, subtraction, and equation, start to the left, work your way over. Negative 14 minus 18, oh, that's negative 32. Add 21, negative 11, subtract 4, negative 15. Fantastic. And this is, again, moving on that number line. Your calculator can do this stuff for you easily, but I think it's very beneficial, one, to know how this stuff works in your head, so that way you can solve without a calculator, and two, not always trust your calculator. Your calculator is as smart as you are. If you don't know what you're doing, your calculator is not going to correct you. So it's important that you get this stuff. All right, application processes. These are word problems. Everyone hates word problems. I know. However, it's important to figure out what's going on here. So let's start from the top and read it. The average temperature on Mercury's sunlit side is 950 degrees Fahrenheit. The average temperature on Mercury's dark side is negative 346 degrees Fahrenheit. What is the difference between these two average temperatures? Well, what am I looking at here? I see a bunch of numbers. I see 950 Fahrenheit. I see negative 346 Fahrenheit. And I also see mathy words. I see difference. I see average. What does this all mean? Well, difference is addition or subtraction. Difference is subtraction, right? So I have 950. And I want to subtract the other number. Negative 346. Is that correct? Or is it negative 346 minus 950? And does that matter? Those are the kind of questions that once you can answer, will give you a better understanding of math, which will set you up better going forward in the future. So am I doing negative 9? Am I doing 950 minus negative 346? Or am I doing negative 346 minus 950? Well, try solving both, right? If I start 950 and I subtract a negative number, subtracting a negative number is adding a number, right? 950 plus 346. Cool. So what is that? Well, do the math in your head or pull out a calculator. Either way, you land at 1296. Sweet. So what happens if I do the other one? Negative 346 minus 950. Negative 346 is the opposite side of 0. So I'm way over on the left of the threshold, and I'm subtracting 950 from that. Funny enough, we get the exact same answer. Should be erase that. Negative 346 minus 950 is simply negative 1,296. So both of those gave us the same number, but one's negative and one's positive. What does that mean? Well, that's where the word problem part of this conversation comes in. If you can do the math and describe the answer, and the answer is the same, it doesn't matter, right? It wants to know the difference between two average temperatures. Well, if you have a negative difference or a positive difference, funny enough, those are still just differences. So for this particular example, the ordering of the numbers doesn't matter because there's a 1,296 degree difference between those temperatures. Cool. Exponents and order of operation. This is the part where we get into math that is important at higher levels. Cool. So what is an exponent? Exponent is a way to define, let's skip a chapter here. Oh, weird. Why is it going from one? I think I remember. This is confused, isn't it? Yep. There we go. Okay. Let's do section 3 before we do section 4. I thought that was backwards. I have to fix that. All right. So multiplication, division. What a multiplication, what a division. Well, multiplication essentially is a way to do a lot of addition. And division is the opposite of doing that addition. So when I say 3 times 2, what do I mean by that? Well, 3 times 2 is either 3 sets of 2 or 2 sets of 3. And here you can see all the different ways to write that multiplication product. But practically, we are just doing the same thing over and over again. So like we'll do 3 by 5 because it's on the screen here. So if I say 3 times 5, that's shorthand for me saying I'm adding 5 3 times. I have a set of 5 that has 3 5s in it. So instead of writing out this big long 5 plus 5 plus 5, I can write 3 times 5, and you know that there are 3 5s I'm adding together. Funny enough, this could also be 5 3s added together. So 5, I think we'll get into this a little later, but 5 times 3 is equal to 3 plus 3 plus 3. Wow. Plus 3 plus 3. Those are the same thing, right? 3, 6, 9, 12, 15. So it's just a shorthand. It's an easy way to describe a bunch of addition of the same thing over and over again. That's all multiplication is. If I change it up and throw negative numbers, it's still the same conversation. So 3 times negative 5 is negative 5 plus negative 5 plus a minus is subtraction. So negative 5 minus 5 minus another 5. I just take 3 steps in the opposite direction to get there. Important shorthand things. Anything times 0 is 0. Anything times 1 is itself. You probably remember that from what, middle school maybe. And anything times a negative number is negative. Any two negative numbers result in positive. Why is that? Because, again, if you take this example here in the bottom right and replace those numbers with what we're dealing with here. So if I say this is a -5, then each of these is going to be a -5, right? But if I replace the front number with something that's negative, as shown here, what I'm doing is I'm placing that negative out front of whatever's going on, times -2, which is -2 plus -2, which of course would be -4, but I have a negative outside the front of it, which makes me a +4. I guess also key point here, these parentheses, these are bent shapes. That is describing something that needs to, within the parenthesis, happen first. That's what that means. So, and again, we'll get to that in here a little bit, but a parenthesis says, pay attention to me, basically, and figure me out before doing anything else. So again, these are different ways to do negatives. Sorry, to do multiplication. And all that's saying is, so parenthesis, pay attention to me first, -8, okay, I have a -8. And I want us to multiply that by -4. So what am I doing here? Well, I have 4 sets, I have 4 individual -8s I'm adding together because multiplication is shorthand for addition, and I'm throwing a negative sign right out the front of it. Again, part of my theory on how to teach math is for have you to do it. So we're going through a lot of this stuff quick and dirty. If you can do this on your calculator, I still want you to figure out how to do it by hand because it's only going to make you better at math. So when you're going through your review examples and your tests and stuff like that, the assignments I give for this class, yeah, you can just punch into your calculator, but it's worth it to know what you did with your calculator. I'm not going to ask you to do the full longhand for every single thing. That'd be kind of redundant. But if you're throwing stuff in your calculator, getting the correct answers and not knowing what you're doing, you're defeating the purpose of getting better at math, because it can come to a point to where your calculator is not going to know what you're doing. And if you don't know what you're doing and your calculator doesn't know what you're doing, you're just going to have a bad time. So more examples here. Essentially, every negative switches the sign, right? So if we have 1 negative, it's negative. 2 negatives switches to positive. 3 is negative. 4 is positive. 5 is negative, etc., etc. Cool. So again, this is suggesting starting from the left and going to the right. I have -3. I multiply by 4 to -12, and I multiply -12 by -5. That's 2 negatives. They flip over to be +60. When you're going through this on your own, take your time, write things out as much as you can. You will find out the more you write, the more notes you take when you're doing your assignments, when you're practicing your math, the quicker and faster you're going to be. If you rush through this stuff, even this basic stuff that you think you get, if you rush through it, you're going to be hurt in the long run by it. Take the time, write it out slowly, make sure you know exactly what you're doing. Cool. So what is division? Division is essentially the opposite of multiplication. And I think the center number here does a good job of explaining that. 8 divided by 2 equals 4, and 4 times 2 is 8, are the same math. They're just in different directions, right? All the numbers are the same, all the relationships are the same. So connecting multiplication, division like that, knowing that they're opposite effects of the same process, is really going to help you understand division and what it does. Division, of course, is cutting stuff apart, right? If I have a pizza and I need to feed 4 people, I divide it into 4 slices, and then everyone gets 1 slice, right? But since multiplication and division are reverses of the same thing, a lot of the same rules apply. Again, here, if I have positives and negative numbers, they interact the same way. If I have an even number of negative numbers, it's negative, an odd number is positive, stuff like that. And let's keep going through the same examples. There's three ways to divide things. Do we go over that example? Not really well. Okay. So the three ways to show that things are dividing are, first of all, this top-bottom approach, where this is read as 12. Give me a draw. There we go. 12 divided by -3 equals -4. That's how you say that, right? 12 divided by -3 equals -4. And then we can also draw it this way, which is -18 divided by -2 equals -9. There's two different ways to write the same basic sentence, right? The third way, which we'll get to in a bit here, is the drawn out version of long division, which sounds scary. Everyone hates long division, but once you do it, you're going to find it has significant benefits. Again, different words, quotient ratio, etc., etc. Cool things about division is division can break the universe. If you divide 0 into anything, you get 0. If you divide anything into itself, you get 1. And if you divide anything over 1, you get itself, and you can't divide by 0. The way I explain this is, again, to figure out what division actually is. What is multiplication? What is addition? What is subtraction? What actually is division? So we said before, addition is kind of moving in the same direction. Subtraction is moving in the opposite direction, right? Multiplication is shorthand for addition. Multiplication is also how things grow, how things expand. So therefore, since division is the opposite of multiplication, division is how things shrink or how things separate, right? So understanding that division is kind of the separation of things explains a lot of these principles. So the top part of the number here, let's use this example here with a 0. The top part is how much I need to give out, and the bottom part is how much I have. So I'm going to use a piece of pizza here, right? If I have 0 pizzas and I want to give it out to my 5 birthday guests, each guest is going to get 0 pizzas, right? Because I have no pizza to give them. The bottom one here, if I have 5 pizzas and 5 guests, every guest gets 1 pizza. Well, what if I have 5 pizzas and 1 guest? Well, then that 1 guest gets 5 pizzas. Well, what if I have 5 pizzas and no guests? Well, I can't even answer the question how many guests get pizzas because there are no guests. The guests don't get, it's not that the guests don't get pizzas, there's no guests even to exist. Let's be honest here, if you have a birthday party and no one shows up, did you really have a birthday party? No, you just had a birthday, right? You have a party with no people. And that's what breaking the rules of reality and dividing by 0 is. That's what dividing by 0 is. Having a birthday party with no people. You can't have a party without people. Don't do that. Don't break the universe. Don't divide by 0. Thank you. So again, I'm going to pause here for just a second to acknowledge this concept. Go through those examples. Use your pause the video. Use your words to describe examples 1, 2, 3, and 4 with pizza and birthday party. I think you're going to kind of get what division is at a practical level. Also worth noting. Let me get a second. Also worth noting at the bottom here, negatives don't really care where they exist in division if you're doing that top-bottom division. Because one negative means the entire thing's negative for that conversation because, again, one opposite changes what you're doing. Go through your examples here. So this could have, of course, also been drawn as, there we go. -120 divided by -8. When we get to long division, I'll show you the third example of how you can divide that, but But to give you a preview, it was this dude. Y'all remember this? Yeah, where the answer's up top. Ooh, that sounds brutal, right? Cool. Yeah, cool. Application problems. Application problems. Everyone loves application problems, right? The daily high temperature in degrees Celsius for 6 days in Anchorage, Alaska were -14, 3, 0, -8, 2, and -1 degrees Celsius. Find the average daily high temperature. So what's an average? I don't remember. Average is when you add up everything together and you divide by the number of numbers. How many different numbers do we have? Well, we have 1, 2, 3, 4, 5, 6 different numbers. So that is 6 numbers. And then what is sum? Well, sum, come here, you. Sum is addition. So we add up the numbers together to get the sum, and then we divide by the number of numbers, which is 6. Cool. Let's do that. So if we add up our numbers as shown above here, -14 plus 3, well, that's going to be -11, plus 0, well, that's going to be -11. Oops, -11 still. Well, then -8, so also like plus -8, which is subtract 8. -11 minus 8 is -19. -19 plus 2 is -17. And -17 plus -1 is -18 again. Fantastic. So -18 divided by 6. You can use your calculator for that if you want, or you could long division it, or kind of whatever works for you, right? We could pizza pie it, right? I have 18 slices of pizza and 6 guests at my party. How many slices can each person get? Well, if I start out with my 6 people, so let's do 6 buddies here. My buddies are going to be squares. 1, 2, 3, 4, 5, 6. 6 buddies. And then each of those guys starts out by getting 1 piece of pizza. This is way overly complicated, but whatever, it's cool. So give a piece of pizza to each of these people. 4, 5, 6. Now, how much pizza do I have left? Well, I had 18 pieces, right? And I gave 6 away. That leaves me with 12 pieces left. So I have more pizza to give. Let's give everyone another piece of pizza. 3, 4, 5, 6. So I've given out 6 more pieces of pizza. Leave me with 6 more pieces. Cool. Let's try again. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. I've ran out of pizza. Therefore, 18 divided by 6 is 3. Because everyone got 3 slices of pizza. So again, that's division. How does it work with average? Well, that's the fun part about these word problems is, and division multiplication math in general, is there's lots of different ways to describe the same thing, right? But hopefully you're kind of getting what the point of division and multiplication are. That's really what I'm aiming at here. So let's apparently go back and discuss exponents order of operation. So now that we know what multiplication and division are, we can talk about exponents. And that, in the same way that multiplication is an easy way to do addition, exponent is an easy way to do multiplication. We have what's called a base and an exponent. And these images are screwed up. Sorry about that. But this is supposed to be a little 5 above there, because there are 5 iterations of 2 multiplying by 2. 1, 2, 3, 4, 5, right? 2 times 2 times 2 times 2 times 2 can be written as 2 base 2 exponent 5, shown here. And again, what that is, an exponent is like a little teeny hat on the top of a number. 2, 5. So looking down here, it's kind of covered up. What should this number be? should be a 4, right? Because it's 4 A's being multiplied together. As with everything we were talking before, there are many different ways to say exponents. To the power of raised to, squared, cubed, all these other things. The more you do it, the better you get at it. I'm going to keep saying that. What exponents do physically is essentially you add dimensions to what you're talking about. That's why we say squared and cubed. If a number line dictates a number squared is a 2D representation of what we're talking about. So a string can be a foot long, but a carpet is a 1 foot square piece, because you go a foot one direction, take a corner to the foot the other direction, you make a square out of it, right? And then 1 cubic foot of something is a 3-dimensional object that has 1 foot on each side. Right? When you go by soil, it's a cubic foot of soil, right? Because if you make a 1 by 1 by 1 garden bed, it'll fill that up perfectly. And that's the complicated version of what exponents do. Super simple definition is just a shorthand way of writing a lot of multiplication. So this on the left and this on the right are the same thing. One of those is easier to write, which is why we use exponents. Just that simple. And again, this is also something your calculator can do, but if you know what your calculator is doing, you're just going to be better at it. This is a good example here, also of parentheses. So if you notice here, we threw the -2 inside the parentheses, which means care about me first. Okay, 2 is opposite. 2 is negative. The 2 in this question is a -2. So every time I repeat it 4 times, each of those is a -2. What if I don't use parentheses? Well, that's what I have here. Since I'm not telling you to care about that negative and that 5 together, that means they're not together. So we can just do left to right. So I have a negative out here, and then I have a 5 to the third. Which of those happens first? As you can see here, the negative is applied at the very end, right? Because these are all positive 5s. The reason why we do that is something called order of operations, or PEMDAS. PEMDAS, this is a word that you're probably going to want to write down on the top of your homework. PEMDAS. And what PEMDAS means is, well, actually, let's get to that in a bit. So PEMDAS, PEMDAS. Keep that in mind. If I mix up my math, because I have right now we've covered addition, subtraction, multiplication, division, and exponents, and we touched briefly on parentheses. Those are all different ways of ordering and simplifying expressions of math, because it's all basically addition at the end, right? Subtraction is just addition in the opposite direction. Multiplication is just a bunch of addition combined. It's all just addition. But since they all are doing the same thing in different ways, we don't want to screw up the way they're doing things, which is where PEMDAS, or order of operations, comes in. And what PEMDAS means, do they have a short version of it? No, okay. So I'll go over here. Yeah, I'll go here to do it. PEMDAS is, what's that called? I can't remember the word, but it's a word where each letter means something different. It stands for, the P stands for parentheses. The E stands for exponent. The M and D stand for multiplication and division. The AS stand for addition and subtraction. And it reads left to right because that's the way you're supposed to do it. Whenever you run into a math problem, you should always remember PEMDAS, because PEMDAS tells you what to do first. As shown in the example here to the left, we look at this equation here. We look at this equation, and we say, okay, PEMDAS, what do I see? What, do I see any parentheses? Yes, I do. I see parentheses here, and I see parentheses here. care about parentheses first. -4, cool, that was easy. -4 just is -4. But this right here is a math equation inside the parentheses. I care about parentheses first. It's the first letter in PEMDAS. Solve that. -3 minus 8 is -5. So I've solved that. Now I can rewrite my equation, having finished all the parentheses, and move on to the next thing. The next thing in PEMDAS is E exponent. Do I have any? Yes, I do. So I need to solve -4 raised to the second power, -4 squared, before I move on. -4 squared is 16. What is squared again? Well, that is -4 times -4. 4 times 4 is 16, but I have two opposites there. So I opposite it twice, so they cancel out really to give me a positive 16. Have I used up all my exponents? Yes, I have. Cool. Now what's next? MD, multiplication division. Do I have any multiplication or division? And noteworthy here, I put MD together because it actually doesn't matter which one you do first. So I do have multiplication. I have here -2 times 5. Well, again, multiplication is really just shorthand for two iterations of -5 added together. So -5 plus -5. That's the shorthand version. That's a longhand version of multiplication. So I start at 0, I go -5 on my number line, and then I add another -5, landing me at positive 10. Oh yeah, okay. So this is equal to -10. Sorry about that. Let me go back here real quick. But then I also have a negative right here. So they skipped a step here, bad on them. This should have in the middle here equals 16 minus -10. Minus negative is a positive. 16 plus 10 is 26. PEMDAS is how you do that. If you just started the left and went right, you'd run into some issues. So let me do the bad version in red, right? This front half really wouldn't have changed, but -2, 3 minus 8. What are you supposed to do about that? Really ugly. What are you supposed to do about that, right? What are you supposed to do about, use text here? 2, supposed to be in red. There we go. 2 parentheses 3 minus 8. Let's see. How are you supposed to solve that if you just work left to right? Are you supposed to do the 2 first? So what, 2 times 3 is 6, right? So 6 minus 8, well, that's -2. Well, -2 is not the same thing as positive as -10, right? So that's why PEMDAS is important, because we need to remember that the parentheses have to happen first. The multiplication happens before the subtraction, stuff like that. Otherwise, you get wrong answers. We don't want wrong answers. We want correct answers. Other important point about PEMDAS is some parentheses are inferred rather than written. Namely, when you have division shown in, I want blue. When you have division shown in this manner, there are inferred parentheses on the top and the bottom of everything. So when you're solving this problem, you need to care about parentheses first, and you actually have 3 iterations of parentheses that you need to solve before doing anything else, which is why they solve for 12, 3, and 2 before going on to the division to 4, before going on to the addition subtraction, get to our answer. So top bottom division has inferred parentheses in it. Everywhere else, the parentheses should be written out. I personally argue when I write these things out, I am not a fan of the division symbol when I'm doing math. Since I write down everything to make sure I don't make any mistakes, I would probably consider this as 6 divided by, and then write out what's going on the bottom. Because that doing it this way tells me something, right? Ooh, actually, okay. So I made a slight mistake here. If you caught it, good for you. The slight mistake was with that guy over there. So this gets a bit into, you know, they drop these things without explaining them well, which is probably my job, right? Square brackets. A square bracket is a type of parenthesis, but the square bracket is do later parenthesis essentially. So I have parentheses inside of parentheses here, right? I have this parenthesis around the -2 and these square brackets. And what this means is parenthesis means do me first, right? Pay attention to me. So but which do I pay attention to? I pay attention to the one most on the inside. So I need to solve this parenthesis, which is what happens here. I'm sorry, which is what happens here. And then I solve out. Let me clean this up and we can go through this in more detail. All right. So -2, good. I can solve that. This is finished. And then I can keep with the square bracket. What's 4 minus -2? Well, that's the same thing as saying 4 plus 2, which is 6. Cool. And then I can care about my exponent, which is what happens here. And then I can care about my division. And then I can care about my subtraction. What I did wrong, just to remind you, is when I broke it up this way, I put this on the bottom. And that was incorrect because the square brackets told me what is being divided by. I am not dividing 6 by -2 to the third. I am only dividing 6 by, get rid of all this jazz. I'm only dividing 6 by what is in those square brackets because I do those square brackets first. And the subtraction sign says that the 2 to the third power, 2 cubed, that happens after I do my division because PEMDAS, right? PEMDAS says, PMDAS, PEMDAS says, do all of your multiplication division before you do any of your addition and subtraction. If you cannot add or subtract anything, you cannot subtract this until you do your division. But the parenthesis says I care about this subtraction before I care about that division because it's inside the parentheses. This is why PEMDAS is important. The math equation is written out in a certain way and only one number is correct. If you screw up the order of operations, you're going to get the wrong answer. All right, so let's skip past this thing we already covered. I really need to fix this. That happens every year. And factoring and prime factorization. Okay, so one of the fun parts about math, as I said, is that it's stepped. So you have to do you have to learn certain ideas and principles before you can move on to the next idea or principle. And at some point, what you learn in the past is the hard way, and what you do in the future is the easy way. Factoring is an example of that. Factoring is the hard version of doing something more advanced. But if you don't know how to factor, you're not going to be able to figure out the easier version later. So you need to learn how to factor something now, so when you go to the more difficult math, you don't struggle. So what is a factor? A factor of a number is a natural number that divides the number with a remainder of 0. Things that don't divide with a remainder of 0 would be when there's things left over, right? You got 3 slices of pizza and you got 4 people. You can't give 4 people 3 slices of pizza and have everyone get the same amount of pizza without affecting the pizza, right? If you got your 3 slices, you hand on the first 3 people, the 4th person doesn't get any food. You could chop up the pizza so that it's a different collection, but then you don't have those original slices anymore. So dividing without a remainder of 0 means everyone gets an equal amount. If everyone doesn't get an equal amount, you don't have a remainder of 0. In this example here, it shows the factors of 12. There are certain numbers that can divide into 12 and have a remainder of 0. Natural numbers, of course, being a key factor here. We're not counting negative numbers. You'll see why. What numbers divide into 12? Well, 12 divides into 12, right? If I have 12 slices of pizza and I have 12 guests at my party, everyone gets 1 slice. Likewise, if only one person showed up, they get all 12 slices. But 2, 3, 4, and 6 also work in the same idea. So 1, 2, 3, 4, 6, and 12 are factors of 12 because those are the only natural numbers that divide evenly into it. Everything else is not even. The way to figure out factors is honestly just to work your way up the scale until you run out of numbers. As shown here, 40, one of my factors of 40, well, 1 is always a factor of everything, right? If you have, no matter how much stuff you have at your party, if only one guest shows up, give all the pizza that one guest. So 1 and 40 are factors, but 2 and 20 are also factors because again, you can divide 40 into 2. Here we have 4 and 10 are factors. Now, what's cool about doing it that way is as we keep going up the number here, we're eventually going to get to a point to where we're repeating ourselves because 4 divides into 5 as well, leaving you 8, right? 6 and 7 don't work, but then 8 divides into 5. So since we have repeated ourselves, which is what's shown by this arrow here, we have found all the factors. As soon as we repeat our factors, we went 5 and 8 to 8 and 5, we've hit them all. Because we can keep going and we'll get 10 and 4, we'll get 20 and 2, and we'll get 40 and 1, but I don't have to because factoring defines itself as being completed once you close that loop. And again, you're gonna be doing some manual factoring and it's going to help you. If you understand how to factor, it's going to help you in the future. I promise you, right? There are various factoring rules, shorthands, if you will. 2 is a factor for any even number, for example, any number that ends in an even digit. So anything that ends in 0, 2, 4, 6, or 8 can be factored by 2. In the same way, if you have a 3 as your ending digit, 3 is a factor of it, right? Actually, no, 3 is a factor of any number where the sum of the digits is divisible by 3. That's what I meant. So yeah, like 63 doesn't divide into 3 evenly, but I think it doesn't it? No, it doesn't. 21. Okay, 73. There we go. 73 does not divide into 3, but 63 does because the sum of its digits are divisible by 3. 6 plus 3 is 9. 9 is divisible by 3, therefore 63 is divisible by 3. These are again shorthand factors. You really just should do. I'm going to suggest doing the brunt work to figure it out rather than try to find every way to save 5 seconds on your homework. 5 is divisible in anything that ends in 5. There you go. So there's some factoring examples. Again, notice how much space they're using to answer these questions. I highly suggest you do the same and use that much space. You're really going to benefit from it. Prime factorization. Prime factorization refers to a number being prime. A number is prime if it's only divisible by 1 in itself. Shown on the bottom there are the prime numbers less than 50. They're unique because, again, they only have one factor. They don't have factors outside of 1 in themselves. Everything's divisible by 1, but 5, for example, is not divisible by anything other than 5 evenly. If you have 5 slices of pizza and 4 people show up, not everyone gets a slice. 6 people show up, not everyone gets a slice. The only way to find out 5 slices of pizza is if 1 person shows up or 5 people show up. We call 5 a prime number then. Prime factorization. This stuff is fun. T-graphs. So prime factorization of a number is expressed. The number is a product of its prime factors. Was it prime factor? Well, again, a prime factor is a number that's only divisible by oneself. So if you have a number like, say, 84, what numbers of 84 are prime and factors? Well, 2, 2, 3, and 7 are all prime factors of 84. Therefore, you can use those numbers to derive 84 in the most simple fashion. What do I mean by that? Well, so if we take 84, we know 84 is divisible by 2 because 4 is even. So that leaves 84 divided by 2 is 42. Well, what's 42? What factors of 42 exist? Well, 42 is a factor of 2 because 2 is even. So I can divide 42 by 2 to get 21. Okay, is 21 factorable? Yes. I can do the long version, or I can notice that 21 is the digits of 21 are 2 and 1. 2 plus 1 is 3, and 3 is factorable by 3. So therefore 21 is factorable by 3. 21 divided by 3 is 7, leaving me only with 7 as a factor, where 7 divided by 7 is 1. I'm done factoring, I'm down to 1. And then those totaled up numbers, 2, 2, 3, and 7, when multiplied together, all equal my original of 84. So what you just solved for essentially is the shortest math problem, the least amount of numbers that you can multiply together to get what you want. 2, 2, 3, and 7, those 4 numbers is the smallest equation that multiplies up to to 84. You can write a bigger equation that multiplies up to 84, but you can't write a smaller one. There are not 3 numbers. Oh, sorry, there are not 3 natural numbers that you can multiply together to hit 84. There are not 2 natural numbers they can multiply together to hit. Well, okay, you can do 2 different numbers, or you can do 42 and 2, obviously, but factorable numbers, prime numbers, that's the smallest amount. You may look at that and say, why am I learning that? That sounds dumb. These things apply later in this class, and they also apply later in more complicated math. So it's good to have these base factors down, right? We're building the foundation of mathematics here. We're not trying to jump straight to the easy solutions at the moment. 3. So what is the prime factorization of 132? Well, we can walk through that process by, I think it doesn't, okay. So what is 132? It divides by 1, because everything divides by 1, cool. Does it divide by 2? Well, yes, it does. 132 divided by 2 ends up being 66. 66 divides by 2 and 33. 33 divided by 2 and 11, 11 and 1. And there we go. Our prime factorization is our smallest equation that multiplies together to get our original number. I promise you, I'm going to highly suggest making these T-charts in your homework and working it through. You're really going to benefit from doing that. Least common multiple and greatest common factor. Least common multiple and greatest common factor are fundamental number quirks that relate directly to factorization and prime factorization. So least common, and again, this is also super useful in like division and stuff like that when we get there. So the least common multiple of 2 or more numbers, the smallest number that's multiple of all said numbers. 24, least common multiple of 24 are 6 and 8, because those are the smallest numbers that are divisible, because 24 is the smallest number divisible by both of them. Nothing smaller than 24 6 can go into, and 8 can go into. That's the point. And tends to be found by doing your prime factorization. So what can you create without like duplicating itself, essentially, right? Finally, these kind of multiple of 10 and 12. Well, what is the easiest multiplication I can do to get 10? 2 and 5. What's the least multiplication I can do to get 12? Well, 4 times 3, which is 2 times 2 times 3, are the smallest numbers. So if we throw all that together, 10 and 12 add up. 10 and 12 don't make 60 in of themselves, but 60 exists in 10 times 12, right? So 60 is the smallest number you can get from the components of 10 and 12. You can get bigger numbers all day long, but 10 and 12 have a least common multiple of 60. Greatest common factor is, well, it's the opposite direction. So greatest common factor is the greatest number that divides evenly into all your other numbers. So what divides both into 36 and into 90? Well, one of my common factors of 36, 2, 2, 3, 3. One of my common factors of 90, 2, 3, 3, 5. So I share 1, 2, I share 1, 3, and I share a second 3 between them. Therefore, 2, 3, and 3, multiply those all together, you get 18. 18 is the smallest number that divides into 36 and divides into 90. And these are all actually very useful tools to have, but you need to know how to get there before I use them. So these common multiple, again, that's the smallest number that everything goes into. And greatest common factor is the smallest number that is part of everything. So least common multiple 15, 20, and 30. And well, 15 is a multiple of 30, right? But 20 is not a multiple of 30, and 15 is not a multiple of 20. So the number is bigger than those three. 20 is a multiple of 40, but 40 is not a multiple of 15 or 30, right? So we can play the game of just like going through the numbers until we hit there, but the better math solution is breaking it down into its prime factorization, and also all those numbers are prime, and then finding things that are common. I see we have a 2 here and a 2 here. Cool, so drop a 2 here. So we have a 2 here, but we don't place out, so that second 2 needs to be accounted for, because I need 2 2s to exist in order to hit 20, right? I see I have a 3 and a 3, so we drop a 3. Because I need a 3 to exist or to hit 15, and all 3 of these have a 5, so 1 5 goes down because a 5 is required for 15, 20, and 30 prime factorization. Multiply those 3 up together, I get 60. 60 is the smallest number that within it as a factor holds 15, 20, and 30. Addition subtraction of rational numbers. Ugh. All right, so I think this is coming to the end. Let me check real quick. Oh boy. All right, we don't do. I don't think we worry about that. Okay. So what is a rational number? A rational number is essentially division. When I said before, there are multiple different ways to write division. One way to write it is that in a line with the little dash and the 2 dots. This thing, right? That's division. And then number on top of a number is also division. And when you write one number on top of another number, we call that a rational number. Rational, ratio, fraction, all the same thing. And you can actually do all of this math with fractions and rational numbers. And if you remember a couple of the tools, and PEM does actually, funny enough, you will find this not to be a very difficult process. Key things to remember here, you can write fractions in many, 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 many different ways and have them all say the same thing, right? 4/6 and 2/3 are the same number. They're representing the same amount of thing. It's just how many different subdivisions do you want, as shown below. So some numbers, however, are the most simple way of saying that. I can say 4/6, but that's doing more than I have to when I can say 2/3 and represent the same answer, right? If I, how much gas, my gas tank is 2/3 full. Okay, I know what that means. My gas tank is 4/6 full. Well, that's just adding unnecessary struggle to it, right? So that is where simplest form comes in common factorization. A simplest form is something that essentially you can't shrink anymore. And simplest form is derived from pulling, as shown here, common factors out. A common factor, as we talked about before, is something that's divisible into everything. So here we have 4/6. 4 is divisible by 2 and 6 is divisible by 2. Cool, that makes sense. So if I divide 2 out of both of those, I can find a number that is the same as 4/6, but more simple. And if I'm going to divide 2 out of both of those, I also can realize that 2/2 is the same thing as 1. So I'm multiplying something by 1, which is its same self. 2/3 multiplied by 1 is, well, 2/3, but 2/3 multiplied by 1 is also 4/6, because 1 and 2/2 are the same thing. That's overly complicated way of explaining simplest form and common factor, but that's what's actually happening in this process. So again, we can use an example here, write 18/30 in simplest form. You could go through the effort of brute forcing it, just trying a bunch of numbers. But again, this is where the common factors is super useful. If I take 18 and I factor it into its smallest prime factorization, I get 2 times 3 times 3. Excellent. I can do the same thing with 30 and then compare those factors. Now I notice here I have 2's and 3's shared. So those can just be blanked out because that equals 1. That's irrelevant. And the only thing that's not shared is 3 and 5. So therefore 18/30 and 3/5 are the same ratio. But just one's a bigger version of the other. Decimal notation. Decimal notation describes well, that's the number version of fractions. So every fraction has a decimal, every decimal has a fraction. And in very basic parlance, the amount of spaces you are behind the decimal equates to a factor of 10. If you're 1 space behind the decimal, you are 1/10 of the way there. Because if you think about it, 0.1 is, it takes 10 of those to equal 1, right? 0.1 equals 1/10 of what you're doing. And then 0.01 is 100th, because if you take 0.01 and you multiply and you add up 100 of those together, you get 1. So this right here, this digit here is 1,000th. So writing 0.043 is the equivalent to writing 43 divided by 1,000. Decimals tend to be easier to do to some people. So, but you're doing the same thing either way. Yeah, here's long division. So this is the third way to do division, as I said before. And this is always confusing because the location of the numbers actually swaps. The top number goes inside the division, and the bottom number goes on the outside. So this is up here, this is described as 5 divided by 8. Down here, it's 8 goes into 5. Right? So everyone remember how to do long division? No, you don't? All right, we can go over this stuff real quick. Long division is actually useful. It's good to know how to do it. And the story essentially is, I try to put 8 in, I can't, I need to move, right? So you start with your number on the outside, and you say, well, actually, I think I have a annotate, spotlight, that's what I wanted. So you have a little 8 out here, and you say, okay, can 8 divide into 5? Well, no, that's impossible, right? Because it's bigger than 5. So then you move 1 step over. Can 8 divide into 50? Well, it can, right? How many times does 8 go into 50? Well, 8 goes into it twice. Yeah, is it going to 3 times? Yeah, is it going to 4 times? Step your game up in that way. What you notice is that 8 will go into 50 6 times, but it won't 7 times. 6 times 8 is 48. 7 times 8, I think it's 54. That's higher than 50. So 8 times 6 is 48. Right here, this is 8 times 6. And then, you remember how to do this, right? Subtract 50 by 48. You land yourself at a 2. Drop the next one down to 20. And then repeat the same process. 8 goes twice to make 16. And then 20 minus 16 is 4. Drop the 0. 8 goes into 40 5 times. This is 8 times 5 equals 40. Remainder of 0. 5 divided by 8 is 0.625. It's a lot. Let me see. I'm going to check the homework real quick. Oh, I don't have you do one of these. Oh, shucks. It's good to practice long division. I know you. you hate to look at it and it sucks, but it's good to practice your long division, I promise. All right, let's move on. Finish this dude up. You have things called irrational numbers. I'm not going to dig into that right now, but that's things like pi, Euler's notation, various square roots. That is not what we need to deal with at the moment. So don't even bother with it. Cool. How to solve complicated things like 90 divided by 168. You could, of course, use your calculator, but this is important to do by hand. So again, there's a couple of different ways to do this. First of all, you could factor it. Secondly, you could divide. Actually, that's a simple form, so you need to factor it. But you could also divide it to find the number, figure out the decimal, whatever you want to do. So I think this is going to factor it. Yep. So how do you factor this? Well, what are the factors of 90? Well, or more specifically, what are the prime factors of 90? When you run through that, you're going to use your T diagram, right? You're going to do, well, I know 90 and 1 factor. Is 2 a factor of 90? Oh yeah, 45 and 2. Is 3 a factor of 90? Oh yeah, 30 and 3, right? Go down that list. Is 4 a factor of 90? No, I can't factor 4 and 90, right? 5? Yeah, I can do, what the heck would that be? 5 and something else. But yeah, so you roll through this process, get all your factors. You're going to repeat at some point. I think you repeat at 6. Oh, yeah, 6 and 5, right? 6 and 5 is 40. So that would be, get over here, you. So that'd be 6, 5, and then 5 and 9. 5 and 9, that's what it was. 9 times, yeah, 5 and 9. 5 and 9. And then you roll it on down. And eventually you land at this. Is it 5 and 9? I'm gonna check that real quick. I'm forgetting my factors. See, I don't have this stuff memorized on the top of my head either. So that's why it's important to do this stuff long form so you can figure it out. 9 times 5 is 45. So it's not. So it'd be what, 18? Yeah, it's 18. Okay. So 5 times 18 equals 90. Yep, good. So we'll switch this out for 18. Is 6 a factor? So 90 divided by 6 is 15. 6 and 15. 7. So 90 divided by 7. So what I'm doing is I'm doing the super long version. Eventually, you're going to kind of figure out the shorthand version of this. Because maybe you've already noticed, 6 is in fact 2 times 3, right? So we are already repeating what we're doing here. We're repeating, that means we're done. Because you can keep this process going. 7 don't work. 90 divided by 8, that don't work. 90 divided by 9, that's 9 and 10. So we got 10, 9. And then, well, then we can do 90 divided by 10, and we've officially repeated ourselves here. All right? These numbers are descending, these numbers are ascending. Cool. So our factors of 90 are, I'm going to text this so it doesn't look so ugly. Our factors are 1, obviously, 2, 3, 5, 6, 9, 10. Those are our factors. But within those numbers, I see factors, right? For example, 10, this is just 5 times 2. So I don't need to write 10, I can write 5 times 2. 9 is just 3 times 3. 6 is just 3 times 2. So my prime factors are 1, which I never really care about, 2, 3, and 5. But in order to get 9, I need a second 3. Because that's the way I create 9. It's 3 times 3, right? 2, 3, 3, and 5 are my prime factors. And then when I multiply all these together, 2 times 3 times 3 times 5, that equals 90. Right? Because 2 times 3 is 6, 6 times 3 is 18, 18 times 5 is 90. That's prime factorization. That really didn't take that long to get our solution. And we did it essentially by hand. We can do the same process for 168. And notice here we cancel out common things, giving us 3 times 5 is 15. 2 times 2 times 7 is 28. 15 over 28 is the simplest form of 90 over 168. All right, so rational numbers, addition, subtraction, multiplication, division, stuff like that. So we know we get what a fraction is and how to use it. Can we do complicated math with it? Well, yeah, we can actually. If you've got that top bottom, that rational number, that fraction, you can add them by adding the top and keeping the bottom. The example shown here at the bottom is if we have 2/7 of something and 3/7 of something, we actually have 5/7 of it, right? Because we add our 2 to our 3 sections and we get a total that is 5/7, even though there are 2 and a 3. So if we have 3/5 plus 3 over 16 plus 5 over 16, well, that equals 8 over 16. Then we can, of course, simplify that down. 8 over 16 was 1 over 2. Oh boy, the least common denominator. We're kind of getting into some weeds here, ain't we? So how can we do complicated math like this? How can we do 5 over 16 plus negative 7 over 40? That looks like a pain, right? But when we're going through this process, we can remember our tools, we can solve out difficult issues. 16 and 40 don't necessarily go into each other, but they both go into something. So we figure out the smallest something they both go into, and then we can find a ratio within that other thing. As shown here, 16 and 40, the least common multiple is 80. You, of course, figure that out via the method that we talked about way back here. I'm not going to go all the way back. So once you know your least common multiple, you can rewrite your equations with that least common multiple. So 5 over 16 is the same ratio as some variable over 80. Right? How do you figure that out? Well, what times 16 is 80, and then do the same thing at the top. That's how you solve that problem. In the same way that, 1 over 4 is equal to 2 over 8. Well, how do you get 4 to 8? You multiply it by 2, right? So if you multiply the top and the bottom by 2, you get the same ratio written differently. So how many times does 16 go into 80? What's that, 5 times, I think? Yep. So this multiplies by 5. This multiplies by 5. So that means 25 over 80 is the same thing as 5 over 16. Of course, we can do the same thing with 7 over 40. And we, get over here, you. There we go. And then we can land all that stuff. Once we have the same common denominator, that's the bottom number. Once we have the same common denominator, we can then add our top part and get a total answer of 11 over 80. Cool. Subtraction, basically the same thing as addition. You need a common denominator, right? So I have 2, 6, and 4, very different numbers. 2 goes into 4, but and 2 goes into 6, but 4 doesn't go into 6. So I need to have a common denominator between the 3 of them. What's the least common denominator of 2, 6, and 4? Well, work at it. What do all 3 of those go into? They don't go into 6. 7, no. 8, no. 9, no. Right? You can brute force this, or you can use your least common denominator prime factorization to get there. Prime factorization would be the factors of 2 are 1 and 2. The factors of 6 are 1, 2, 3, and 6. And the prime factors of 4 are 1, 2, 2, and 4, right? So what is shared between all of them? 1, which I don't care about. They all need at least 1, 2. 4 needs a second 2. And 6 needs a 3. Because
one in itself are not relevant to this conversation. So what's 2 times 2 times 3 equal? Well, 2 times 2 is 4, 4 times 3 is 12. Least common denominator is 12. There you go. And then once you know that, then you can multiply all your components to get what you need. 2 goes into 12 6 times. So I need to multiply the top and the bottom here by 6. 6 goes into 12 2 times, so top and bottom by 2. And this is 3 times. Gets me my common denominator, and then it's just minus 6, minus 10, plus 9. Simple math, simple addition. Bam. 7/12. Again, I'm going through this kind of fast because I want this as a template for you to go back to if you need help. If you, the best way to actually learn how to do this jazz, I promise you, is just pencil and paper, write it out, be explicit in what you're writing. That's how you're going to solve these problems. So I'm not going to do this one. Pause it, read it, try to solve it. When you think you have your answer, fantastic. Does it match up to this? All right, multiplication division is the last thing I think we're going to cover. And that is easier than just subtraction, funny enough. So how do you multiply fractions? How do you multiply rational numbers? Multiply straight across. Multiply all the tops together, multiply all the bottoms together. It could not be easier, right? Negative 3/4 times 10 over 21. Well, multiply your tops together, multiply all your bottoms together, right? If you factor it as you multiply it, you'll land at your least common, you land at your most simplest form, whatever works best for you. But remember, for multiplying fractions, multiply straight across. Same song and dance, right? They break into prime factorization, so the result is automatically the simplest form. Cool beans. If you don't know how to do this on paper, you're going to screw up when you use a calculator to do it. And if you screw up with a calculator on something important, that's not good. I know a lot of the people taking this class are nursing majors, right? Don't screw up my dosage calculations because you forgot how to multiply and find simplest form. Don't do that. I'm not going to be very happy when you give me the incorrect amount of medicine. Division of fractions, you flip them. What that means is, again, division is the opposite of multiplication. If you multiply straight across from multiplication is straight across, division is the opposite of that. It's like going straight, you slant it down, you flip things around. Again, here, dividing 3/5 divided by 5/6 is the equivalent to 3/5 times 6/5. So we're just taking, instead of multiplying straight across, and multiplying cross-like. Shown down here at the bottom is the big example of that. Essentially, we're just trying to dispose of, let's get rid of this here. The thought process besides what this is remember, anything divided by 1 is itself, right? So if we take our division and we draw it as a rational number itself, so we have a fraction at the top and a fraction at the bottom of our entire fraction, that will give us a fraction at the bottom. And if we can make the fraction at the bottom 1, then that's really easy division. Anything divided by itself is 1. How do we make it 1? Well, you need to have like numbers in the top and the bottom here. So 5/6, multiply that by its reciprocal. Reciprocal is when you take a fraction, you flip it, multiply by its reciprocal. 5 times 6 is 30, 6 times 5 is 30, 30 divided by 30 is 1. Bam, problem solved. If a denominator is 1, you don't even write it because that's obvious. So then you can just care about the top, which is going to be 3 times 5 over 6 times 5. Important note here, I'm going to go back a little bit. Notice that both the top and the bottom are multiplied by 6/5. That is because math, you don't do anything in math if you do the same thing to everything. If I see how can I explain this? When you're not changing anything, if you do the same to everything. If you are painting a room in your house, right? And it's a white room, you paint one of the walls blue, that's an accent wall, right? But if you paint all the walls in the room blue, none of the walls stand out anymore. You're not accenting anything else. So it's still all the walls. Wow, lost my words there. All the walls in the room are the same color because you didn't do anything to make anything stand out, right? You didn't add anything to it. You didn't subtract anything away from it. You did the same thing to everyone. You treated everything equally. So that's what's going on here. If you multiply the top and the bottom by 6/5, you are applying the same ratio to everything. So the numbers themselves aren't changing. The ratios themselves are not changing. The numbers are, but they're still defining the same basic thing, right? Another example of that, if I have 1/2 and I multiply the top and the bottom by 2, I get 2/4, right? 2/4 is the same ratio as 1/2, so I didn't change anything by multiplying the top and the bottom by 2. It's still the same ratio. The numbers are different, but it still represents the same basic concept. And that's a very important factor of math I'm going to stress you have to learn. If you do something to one side, you don't want to change, you do the same thing to the other side. When we get, I think, chapter 3 and 4, rational numbers and stuff like that, that's going to become super important. So if you're solving a problem, not changing something, treat everything equally. I'm gonna let you do that on your own. Remember, if it's division, flip it, right? All right, closing up to the end here. Percentages, fractions, decimals. A percent is something out of 100, right? Cent is a penny is a cent, and a penny is one 100th of a dollar. It takes $100 to make 100 pennies to make a dollar. So percent means out of 100. 27% is 27 divided by 100. There you go. You can go back and forth between percentages and fractions. You can have fractions and percentages, as long as you remember that percentage sign is equivalent to saying whatever is in front of it, drop 100 below it. So it was 130 as 130% as a fraction and as a decimal. Well, 130% as a fraction is 130 divided by 100. That percentage sign simply means divided by 100. 130 as a decimal is multiply it by 100th, which is 0.01, 1.3. What is application problem? Again, I'm going to stress you try to do this yourself. Write it out. Don't skip any steps. If you skip stuff, you're going to be upset at yourself. The point of this class is to give you those tools and sharpen those tools so you can solve this jazz. All right, that is the story. Thank you for watching. If this is useful, cool, like, not like, oh Lord, I don't care about likes in this video. Comment, shoot me an email if you got any questions, and thanks.